You have things for me. Chapter 1, section 2. One of the options we have when dealing with graphs is the way we set stuff up. We created a graph, and Stas, this was a question you asked me on Wednesday. Couldn't there be more than one edge connecting things? Well, I really want to differentiate between graphs that allow that and graphs that don't. So I'm going to say a simple graph can have only one edge. Well, at most, right? At most. Between any pair of vertices. So there'll be some vertices that are disconnected, some vertices that are not adjacent, I should say, and some vertices that are. And that'll be a simple graph. If I want to allow more than one edge to join the same two vertices, I'm going to call that a multigraph. So I'm going to draw a very, I hope, very simple graph. I'm going to draw P2. P3. That's a simple graph. If I try to add any other edge except the edge from one end to the other, which would make it C3, right? Make it a triangle. I could either make it a triangle, but any other edge between the two vertices that are already connected would make it a multigraph. There. That's still, quote unquote, a path, but now there are two roads in the middle there. In a lot of graphs, this is actually more useful. I want to go out of this room into the hallway. There are three different ways I could do it, right? There's this door here at the front, that door here on the side, and that door there at the back. This room is connected to the hallway three different ways. That's not indicated up here. The room is connected to the hallway one way. Here it's connected twice. I could add more edges to represent the more doors, right? We call those parallel edges. So, simple graph, single edge between any possible pair of vertices. Multigraph, more than one. You asked me about something else as well. Remember what that was? Well, in this case, because they're undirected, there's no difference. The edge going from A to B and the edge going from B to A is exactly the same. There's no difference between them. It's a road. It's not a one-way road. It's a two-way road. But I didn't write it. Well, I said any pair of vertices. There should be one more word in there. Any pair of distinct vertices. So what would it mean to have an edge between a pair of non-distinct vertices? I promise that's not a vacuous question. What does it mean? Talk about an edge that connects not distinct, indistinct vertices. No, an edge only goes from one vertex to one vertex. So you can't pass through all of them. Those would be different edges, right? Like in that simple graph top there, technically an edge goes from the left vertex to the center vertex. A different edge goes from the center vertex to the right vertex. So those edges are distinct. Now I'm talking about vertices being distinct. Start at this vertex. I come back to the same vertex. Such a vertex is called a loop. I have not said anything about loops in simple graphs or multigraphs. Loops are not allowed in either of those. If I want to allow a loop, I have another different category, a pseudograph. Is a multigraph that could allow loops. So really, in some textbooks, you'll see the word graph covering all of these categories. And they will specify simple graph. This textbook uses graph to mean simple graph by default. So when I want to talk about multigraphs or pseudographs, I need to talk about them specifically. Otherwise, if I just say graph, we're going to assume simple. Page 27, figure 1.35. All of these are multigraphs and pseudographs. All of them are pseudographs. This one has loops. These don't. This one doesn't. These are multigraphs, but not pseudographs. And this is a simple graph. So we kind of think of a Venn diagram, right? Graphs is the umbrella term, pseudograph, and then inside that is multigraph, and inside that is simple graph. And I have lots of parallel edges. I mean, here I've got 3 of them. Here I've got two of them. Here I even have loops that are parallel. Oh, that's crazy. But it works. So going from a vertex to itself makes that a loopy vertex. There's a cartoon on my office door. It shows a disconnected vertex. So you've got a graph. And then over here you have a vertex. All alone. An isolated vertex. Except he went a little loopy. I didn't put the cartoon on my door. They did that for me back in 2017. I just haven't taken it down yet. If I have more than one edge between vertices, I'll need to indicate that. I can't just write vertex 1 to vertex 2, can I? Because there's the upper path, the lower path, the middle path. There are all sorts of different options. I'll need to name them somehow. There are lots of different ways to do this. Most often, I will literally write on the graph. This is edge 1, this is edge 2, this is edge 3. So if I go back to those pictures we were looking at, I could write edge 1 and edge 2. I could write loop 1 and loop 2. Here, edge 1, edge 2, edge 3. Then over here, I need to name those differently too as well, right? So it'd be edge 4 and edge 5. But edge 4 and edge 5 connect the same two vertices. Okay. Same thing here, 1 and 2, 3 and 4. I find it easiest to actually label the graph itself, just like we labeled our vertices. Now, the homework you got back asked you to connect two numbers if either their sum added to be one of the other numbers or the absolute value of their difference added to be one of the other numbers, right? That's two different conditions. So what if I went ahead and used two different edges? Then I'd see all the ones that added to other things with edges, and, oh, 3 plus 5 gives me 8, but it also, 3 minus 5 is 2 in absolute value, so I can add them both that way, right? I'd get two edges between 3 and 5. This pisses me off. Because if those edges are supposed to be different things, they should somehow be coded to be different. Make one of them red, one of them blue, make one of them solid, make one of them dotted. Somehow indicate this to me. Not required. And this diagram doesn't, but that works. We will see other places and other graphs related to these ideas where we do code the edges differently depending on what they mean. That's not something for this course. That's less useful here than it is, say, in Kaylee's work in group theory. So we'll see it in abstract algebra if you're taking that course. We do a little of that in linear later in the course in some other pieces. We did a little bit of it in discrete, but most of the time we just use one color, one style of edge. We'll find a place to make them different later. Questions? So I now allow my city map to look like the city of Pittsburgh. Roads are all sorts of up, and several of them go exactly the same places, and we can get there from here lots of different ways. And sometimes you can't get there from here at all. On the other hand, the other thing that I know happens an awful lot in the city of Pittsburgh are one-way roads. Now, Stas, the edges are different. An edge from 2 to 3 is different than an edge from 3 to 2. So I'm not even call them edges anymore. I'm going to call them arcs. So instead of using a set to indicate the edge between U and V, I'm going to indicate the edge from U to V. In which case I need to change my descriptor. U and V are not adjacent to each other. If I have UV, V is adjacent from U, and U is adjacent to V. There's an orientation here. They're not adjacent to each other. I'm only going one way. Now, in a digraph, parallel edges might not go the same direction, right? And they're not parallel anymore. So here's a weird statement. Remember this graph we had earlier, this multigraph? Let me go ahead and name these. We're going to call this vertex A, and this vertex B, and this vertex C. If this is a digraph, every one of these arcs has to have a direction. You can't have some that are with and some that are without. In a digraph, there are no edges, there are only arcs. So that means each of those needs to go from a vertex to a vertex. How do I indicate that on this picture? Easiest possible way. Use an arrow. There. I don't even have to do the whole arrow. I just have to do the arrowhead on the edge itself. At this point, this is called an oriented graph. Each edge has an orientation. I know which way it's going. Wait a second. That's not right. Each edge has a direction. Now you'll notice I have both BC and CB in this graph, yes? There's a two-way road. Well, there's a pair of one-way roads going in opposite directions. But I can get out of A, I just can never get back to it. Once I leave A, I'm screwed. I go back and forth between B and C all I want. I can never get back to A. It's a one-way road, you're in trouble. If for any pair of distinct vertices, U comma V, at most one of UV or VU is in the set of arcs, which I still call E because I didn't want to use A. I'll use it for something else later. Then D is an oriented digraph. Now, what does that mean? that means that the picture I drew is not oriented, because I have BC and CD. An oriented graph is only connected by one-way roads. If I had a regular graph, a simple graph, then that would only have one edge between any pair of distinct vertices, right? If I start with a simple graph, I could take that set of roads and put a bunch of one-way road signs, yes? I could put a direction on each edge. Let's do K4. What's K4? A complete graph with 4 vertices. I'm going to cheat, and instead of drawing those vertices as a box, I'm going to draw a triangle with one in the middle. That's K4. Why did I do that? Instead of drawing the box. Because I'm a twisted, sick mother. Well, yes, but that's not the reason. What didn't happen here? None of my edges cross each other. So I found a way to draw that without crossing it. I could have drawn the box and then drawn one diagonal and drawn the other one on the outside, right? But most of the time when we draw the box, I think about drawing the X in the middle. I don't want to do that. I like this. That's me. You can draw the box and then one on the outside. Go away, bug. Right? That also has no crossings on it. Whichever picture you like. Put an arrow on each edge. Any arrow you want. Now, wait a minute. There are 6 different edges there. You get 2 choices for each one, right? That's 64 different possible ways to label these roads. You decide. Guess they get to call me Beelzebub today? Lord of the Flies? No way, fly. Excuse me, I'll be really biblical about it. Baal Zevuv. So I start putting arrows down. I don't care which arrows you put where. It's literally irrelevant to me. Now here's a question for you. And I don't know the answer because I just made these up. Are those 2 the same map? I don't know. I literally don't know. I don't think so, but I'm not sure. So that's a real question now. Remember, one of the questions we have is, because I can draw the picture any way I want, is did I draw the same picture twice? I can't tell. I don't want you to try and answer that question right at the moment. We'll be here for quite a while. It's not worth it. And I don't know if I drew the same pictures that you drew. My picture may be very completely different than yours. What I've done, though, is I've created an oriented graph. Every one of my edges, every pair of distinct vertices has one at most edge from one to the other and not the other way. Every pair of vertices is connected by a one-way road. That's called an orientation on my graph. So if I start with a simple graph G, and I put all these one-way signs on it, then what I've done is I've created an oriented graph. I've oriented, or I've created an orientation on my simple graph. Why would you do this? What possible reason could I have for creating an orientation like this? Anybody play chess? When you play chess, you go to move a piece. The way it moves depends on what piece it is, right? You move a rook, you can move them as far horizontally or vertically up your 8x8 board as you want. You move a knight in an L shape, 2 then 1. You move a bishop diagonally. You move a king any direction you want, 1 space. You move a queen any direction you want as far as you can get. How do you move pawns? Either if they're at the starting line, they can move 1 or 2 forward. After that, they can only move forward or take forward diagonals. Every other piece can move in both directions. I can move a rook all the way up and then all the way back. Can't move a pawn forward and back. That movement is one direction. If I think of the vertices of my graph as possible arrangements of pieces on a chessboard, then pawn moves are oriented. But rook moves are reversible, aren't they? So that graph is not going to be an oriented graph. It's going to have the possibility of going back and forth, right? So what happens when you start playing games where all the pieces have unidirectional moves? You can't move back and forth like that. Games like Go are distinct in their orientation. Sorry, games like backgammon. You only move your pieces in one direction around the board. Now you can get sent back, but you don't make that move. Your opponent makes that move. Your moves are always forward around the board. I have not played Mancala in probably 35 years, but I seem to recall Mancala works the same way. You only move one way around the board. I'm sorry? Yeah, but there are still places where you get dropped, right? So you can be forced back, but you don't move back. As a matter of fact, the snakes and ladders board itself is a graph, the board. If you land on this, you get to bypass and shortcut. If you land on this, so that's a graph theory game. If we go back, remember we were talking about coins and positions of coins on a 2x2 grid? We have these coin grids here. Well, there are 12 different positions. But now I'm going to impose a rule. And the rule says you're only allowed to move right or up. You can move a coin from left to right. You can't move a coin from right to left. You can move a coin from down to up, but you can't move a coin from up to down. What happens to my states? There are some vertices where arrows point in and out. There are some vertices where arrows only point in. There are some vertices where arrows only point out. If I'm only allowed to move a coin up or right, and I'm here, I can move up either coin. But I can't get to this position from wherever I am, because if I was at any of these others, to get here, I'd have to move down. So look at C12, and you see both arrows come out of it. On the other hand, I think it's C9. I've already moved to the right, yes? Are there any moves you can make from here? Can't move up. You can't move right. So there are no arrows that come out of this one. There are only arrows that go into it. The terminal position in your game. Again, this is a very contrived example. And the average chess program doesn't have all of the possible positions of the board mapped out, because that would be a huge number of options, right? There are 64 squares. Some of them can be occupied by some pieces, not others. I don't want to think about how many options there are. So rather than store all of them and look at this, it builds my graph dynamically at each step of the game, depending on how far you let it think ahead. How many moves forward should I make? If I make this move, then you're going to make this move, then I'm going to make this move. 3 moves ahead, I could have 1,000 million options already. Faster parallel processing allows us to do that in real time. And modern chess computers beat human players because they can think further out, faster, and weigh the options better. A number of years ago, IBM's Watson computer was on Jeopardy. Anybody remember this? If you haven't, go look it up. IBM's Watson computer played Jeopardy against the longest running Jeopardy champion, Ken Jennings, and whoever the second place person was, whose name I've forgotten, unfortunately, and won because it could think further ahead faster, respond faster. When it played chess, it beat the human grandmasters. The first chess computer to do that was a chess computer by the name of Deep Blue, and it beat Garry Kasparov. Garry Kasparov was the most well-known chess champion for the entire 20th century. Kasparov and Karpov played more games of chess publicly and made newspapers for decades. Now, mind you, I was this tall when they were playing, but still, it was amazing. Karpov came to the University of Miami and took on 36 chess players, and just walked around one after the other and made a move on each table. And by the time he got back around, you should have gone. I lost in 5 moves. I think I was second out, not first, but it was close. I think it was, I don't remember which one it was, but he played 36 people, and I was one of the schmucks in the audience. So I played that one. Now, I think the longest game took less than 20 minutes. But he just kept walking around the circle and making another move, I lost badly. Some of these people put up at least a decent fight, but it's this routine. And he's thinking that far ahead and that far out the game by knowing what moves are permitted and what's allowable. Is that what it was? Okay, I take it back, Stas. The more I think about it, the less sure I am of who the chess champion was, but he played all 36 of us. I think it was one of those two. I just don't remember. Now, mind you, this was the 1970s, so it's been a while. Somewhere there's a picture in the Miami Herald. I'll see if I can find it. I'm sure if I was in the picture, my mother has it somewhere. But this is pre-internet, so it's not digitized easily. So there are lots of variations on our main categories of graphs. Even with all of those, I still want to be able to try and make some definitions and some understandings about the way in which we figure out whether graphs are the same or not, whether I've drawn the same picture different ways. How do I keep track of those? Most of what I will start with is done for simple graphs. So by default, I'll use just the word graph. It'll mean simple. If I want to talk about a multigraph or a pseudograph, or even a directed graph, I will have to say so. By the way, you can have directed multigraphs. You could have a directed pseudograph if I put a loop on there, right? I just have to make it a one-way loop. So directed is a separate adjective from the other descriptors. Lots more vocabulary to throw at you. Between all the different types of graphs and how we put them together and all these different options, I now think we have a decent vocabulary. So let's actually start doing some math with these. I have 12 minutes left. So I'm going to give you two terms, and then I'm going to let you go early. Write it down. That means you all owe me 10 minutes somewhere. I need to count how many edges are adjacent to a vertex or incident on a vertex. I need to know in a directed graph if they're going out or going in. So somewhere I'm going to try and put some numbers to counting edges and counting vertices and counting all of these things. And right now we only have order and size, right? Order is the number of vertices, size is the number of edges. If I want to talk about the relation between those, I need something called degree. And the degree of a vertex can be broken up with a directed graph into two different degrees. Degree in and the degree out. So we're going to get a lot more discussion on degrees on Monday. I hope you all have a wonderful week. I will see you then.
For your first time cycle.